possibilities for lithium metal. There's a lot of excitement about pairing lithium metal in all solid-state batteries with conventional cathode materials, and they can unlock quite a bit of capacity on the order of about 1200 watt-hour per kilogram. And then there's entirely new concepts, right, of lithium air and lithium sulfur batteries. And the idea there is to replace the cathode with sulfur or oxygen, which being incredibly low cost and as well as lightweight, will give us very high capacities on the order, again, in lithium sulfur, 2600 watt-hour per kilogram, lithium oxygen, 3500 watt-hour per kilogram. So I'm going to review some of the opportunities and challenges with these technologies. So all solid-state batteries, like I was mentioning, there's a lot of excitement about this, especially for electric vehicles. There are a couple of companies now that are startups in this space that are valued at several $100 million, even $1 billion, and they involve. So if this is a conventional lithium-ion battery in a all solid-state battery, you end up replacing the anode with lithium. So instead of using a graphitic anode, use dense lithium, and then the electrolyte is replaced with a solid electrolyte. The challenges with the system, again, if this ends up being true, or if this ends up being scalable, this is an incredibly powerful combination. But the challenge with the system is to use lithium metal anodes. Lithium is incredibly reactive and forms a complex interface with the cathode and with the electrolyte, and there's a lot of interfacial reactions. And then the reversible deposition, the plating and stripping of lithium tends to result in dendrite formation. And then ultimately, there are a lot of volume changes going on as lithium is being stripped and plated, and this will result in these components, the solid electrolyte and the anode, or the solid electrolyte and the cathode, losing contact. So again, it's imperative to keep these in physical contact throughout the cycling. And again, this involves typically having pretty high stack pressures and pressing these layers together. So this is a very promising technology, and perhaps the closest to fruition if the problem of reversibly plating lithium anode without dendrites becomes a reality. So taking a step back, what is the fundamental challenge with using lithium? It comes from its electrochemical properties. So lithium metal anode, as you know from your studies of electrochemistry, right? So lithium metal anode it doesn't desperately, lithium wants to give up its electron, and so it is a very strong reducing agent, right? So any electrolyte it comes into contact with is essentially going to react and form some sort of a layer, typically called the SEI layer at the electrode interface. And this comprises a bunch of different species, typically amorphous species that include lithium oxide, lithium fluoride, lithium carbonate. So these electrolyte degradation products together will form a passivating film. The passivating film is typically permeable to lithium ions, so lithium ions are typically still going across it, but it gives rise, or if the SEI interface is not good, it results in a whole lot of challenges that I'm going to graphically show you in a few moments. Fundamentally, the SEI layer, as the lithium changes, is being stripped and plated, the volume of the lithium is going to change. The conformal SEI layer on the surface oftentimes will crack, and the cracks will appear in different places, and this will result in unequal lithium plating in the regions of the cracks, which will then result in dendrite formation. This is a major problem. Over multiple prolonged cycling, you end up getting SEI layers that can be highly irregular and several hundred nanometers thick, as much as several hundred nanometers thick. And then some of these layers will start getting pinched off and creating these regions of dead lithium, right? So a couple of problems to note. the lithium metal continuing to react with the electrolyte to form this SEI layer is consuming lithium from the electrolyte without any actual storage. It's just a chemical reaction that is parasitic. Number two, as this reaction continues, regions and dendrite formation is initiated. Regions of lithium essentially get pinched off and become dead lithium. They're no longer electrically connected. They're surrounded by the SEI. They're no longer electrically connected to the lithium metal. Also, another problem that happens as this sort of dead lithium and SEI accumulates, you end up having a very large polarization, very large buildup of interfacial resistance at this interface, which is also not good for the functioning of the battery. So really a perfect, what people have been really trying to get is a SEI of a proper thickness, which is thick enough to stop further reduction of the electrolyte, but not so thick that you increase the lithium ion diffusion resistance too much. You want to have a SEI that has high ionic conductivity to reduce diffusion resistance and good mechanical performance to accommodate the non-uniform volume change during repeated lithium deposition and stripping. And then it should be able to be somewhat flexible to accommodate these changes in the volume, but hard enough to prevent lithium dendrite from penetrating through. So lithium dendrite's relatively soft, and there is a famous model by Newman and Monroe, which essentially said that if the elastic modulus of the electrolyte is 2 times the shear modulus, you're going to be able to shut down dendrite formation. And so having a relatively good mechanically resilient and robust SEI layer will help shut down dendrite formation to a large extent. And then ultimately you want a dendrite that does not constantly crack and reform, that is stable in morphology and is able to breathe along with the anode as it changes over prolonged cycling. But this is a tall order. This is really yet to be, the full wish list is yet to be achieved, right? And there's a lot of research going on this idea. How do you get a better SEI by design? What sort of additives can be added? And ideally the SEI should be pliable, mechanically resilient, and durable, right? So here's a SEM image of columnar lithium electrodeposition. That's what the dream is. You want to have this take place over hundreds of cycles, a few thousand cycles, without having dendrite formation, but it's very hard to prevent this. And this graphic here schematically illustrates a lot of the challenges. So lithium is a conversion electrode, unlike graphite and where you've got a host. So the large volume change that happens can result in dendrite formation, and the dendrites that can form can go all the way across the cell, resulting in a short circuit. That's of course the most catastrophic thing that can happen. But oftentimes instead you've got the formation and cracking and the reformation of the SEI, and ultimately pieces of lithium get covered with the SEI and either fall off or form a dead layer on top of the electrode that's dead lithium. And then of course again at these tips that are growing, the dendrite tips, the tips, because of the sharpness of the tip, you can have very strong electric fields, and those electric fields at these bare tips can result in further electrolyte decomposition reactions that continue. And the overall result is as the surface gets fouled and you have these complex SEI layers form, is increased polarization of the cell. Again, what happens with dendrites? If the dendrite actually ends up going across, there's this large current, and then in the case of liquid electrolytes, this is of course incredibly dangerous, and it requires the flammable components can the temperature increases, the flammable components can can catch fire. The cathodes will decompose most of like lithium cobalt oxide and release oxygen that will further fuel the fire. And so a combination of oxygen, flammable organic solvents, and heat is a perfect recipe for disaster. Many of you have seen pictures and videos on YouTube and such that show the devastating consequences of these lithium battery fires. And we've seen this now, not just in consumer electronics, and these are pretty bad. Laptops catching fire, cell phones catching fire are pretty bad. But when you have entire cars catching fire, that can be, or large scale grid level facilities catching fire, that's a complete, disaster. That is a humongous problem. So this is something that we have to learn how to prevent. So several strategies. Again, there's probably several hundred research groups across the world working on in industry and in academia, trying to work on preventing dendrite growth, just this problem. There's different strategies. There's these 4 that I reviewed here from this review article by Shen et al. And one of these ideas is the idea of having a structured anode where you try to get selective nucleation and growth of lithium along a pattern framework so that it doesn't form these runaway dendrites. There's a big push to use electrostatic shielding, for instance, where you add something like a cesium ion that is attracted to the tip and repels new lithium from coming in. And by repelling these new lithium from coming in, you essentially give a chance for lithium deposition to happen elsewhere, and the tip gets absorbed into this growing plated system. There's also a lot of interest in using alloys of lithium with bismuth and tin and silicon, but if you end up losing capacity, but if you can prevent dendrite formation, that would be okay. Again, perhaps the 2 most popular methods, and there's a lot of work going on here, is trying to come up with relatively mechanically resilient SEIs. So trying to, instead of letting the SEI form randomly and having a distribution of products, controlling what exactly forms in the SEI. In particular, lithium fluoride is something that people like because it is quite mechanically relatively harder, has a high shear modulus, and therefore you can prevent dendrite formation to some extent. There's some work on using. There's some work that is going on in cycling lithium metal in a different electrolyte from which it is ultimately used. So you end up using something like lithium sulfide and lithium nitrate and creating a SEI layer, and then taking that electrode out and then putting it into some sort of a other cell with an entirely different electrolyte combination. So really tailoring this first few cycles in some electrolytes so that you get the type of passivating film you want at the SEI. So this is a method that is even finding some commercial use at this point, right? And so pairing lithium metal with something like a NCM electrode in a all solid state battery is very promising. But again, perhaps there's a lot of the greatest sort of promise is in unlocking entirely new cathodes like sulfur and air. Right? There's a lot of promise here. Okay, so the fundamental idea of a lithium sulfur battery, you've got lithium metal. Sulfur directly cannot be used as a cathode because it's insulating. So you have to use it with some sort of a conductive material so that you could get good electron transport. People will typically use porous carbon, all sorts of graphitic materials, and then and they store sulfur inside these materials and have an organic electrolyte. And then lithium essentially gets as lithium comes in, the sulfur forms a range of lithium polysulfides, and so you end up going through these multi-electron redox reactions. Lithium air battery is instead of, again, this is a conventional lithium cobalt oxide battery. Lithium air battery, instead of sulfur or lithium cobalt oxide, uses oxygen directly from air, and you can essentially reduce the oxygen to form either some sort of peroxide species or to form, in the case of an aqueous electrolyte, lithium hydroxide. Okay, and again, very attractive concepts that have very high metrics. So current lithium ion, this is the capacity, as you can see, 387 watt-hour per kilogram, and the theoretical energy density is here. Zinc, lithium sulfur can be much higher, about 2200. Lithium air in a non-ecosystem can be 3500. So really high capacities can be unlocked if you end up using this. So lithium sulfur is more advanced than lithium air, but still not yet at prime time. So the point is that you can take sulfur S8 and reduce it by forming these lithium polysulfides, and you go through a sequence of reactions. So lithium to S8, lithium to S6, lithium to S4, and then lithium to S2 and lithium sulfide. Now these two products are fine, but they're solid insoluble products. These are soluble products, and this is a problem. So like I mentioned, sulfur directly cannot be used as an electrolyte. So you have to, neither sulfur nor any of these products are electrically conductive. So you have to pair these with some sort of a conductive host, typically some sort of a carbon material. And then what ends up typically happening is that these products being soluble come out of the host and will even go across the separator and deposit on the lithium metal anode. And this can be a major problem. So there's multiple issues plaguing the use of lithium sulfur. One is this polysulfide shuttle. These soluble lithium sulfides get dissolved into the electrolyte. They pass through the separator, and then they deposit, and they actually even pass through the SEI I was just talking about, and they will corrode the lithium metal and form all sorts of other films. Of course, using a lithium metal, the dendrite formation that entire problem still has to be solved. And then the other challenge is that, again, because of the insulating nature of sulfur and discharged products, you end up not being able to use just sulfur. You end up losing a lot of capacity because you're using sulfur loaded onto some sort of a host lattice. And really, there was a lot of promise about, in the last decade as people started exploring this chemistry. Some of this promise has turned to disappointment because there's some real big challenges in scaling these into pouch cell levels. So this has been a huge problem. So typically, what will happen is a mesoporous carbon electrode is loaded with sulfur. Mesoporous because it's got lots of different porosity to accommodate sulfur, okay? And it's got, and it's conductive. And then it's put in, it's combined with a separator and an electrolyte and lithium metal. But then again, you've got to deal with several different challenges. The problems of lithium metal dendrite formation, having good cyclic efficiency, the formation of these insulating lithium sulfide layers from the sulfide polyshuttle, the polysulfide being transported across, and then having a good SEI layer, and then the safety issues of the dendrite, finding a good electrolyte that is stable across this window, and that doesn't have very high solubility for these polysulfides to dissolve them, and then to be able to trap these discharged products, including the soluble ones, and to prevent them from going over or getting into the electrolyte or going over to the anode. So lots of different strategies, again, from the perspective of functional materials. There is a lot of different strategies that are being unveiled to essentially prevent this polysulfide dissolution and shuttling problem. Part of this idea is to have some heteroatoms like nitrogen atoms and such in the carbon lattice that can interact with the polysulfides. Another idea is to use separators that are ion selective membranes that allow, for instance, ion transport of lithium ions, but prevents these polysulfides from going across. So having a good separator that can control sieving, that brings in electrostatic repulsion, These are all issues. Another pretty nice approach that different groups have come up with is accelerating the transformation of polysulfides, accelerating this into the insoluble products, trying to get there as quickly as possible so you don't have a chance of these polysulfides being leached out of the mesoporous cathodes into solution, right? Okay, lithium air batteries, again, very promising, a fantastic concept, but still lots of challenges that remain. Once again, since you're going to use lithium metal, dendrite formation is an issue, safety is an issue, you need to control the SEI phase, cycling efficiency is an issue. But then on the side of the cathode, you also need to have a catalyst that is able to, so the kinetics is a major challenge. You need a catalyst that is able to effectively reduce the oxygen. So what catalyst will you use, the diet distribution, the loading, how do you have a pore size that allows for this oxygen reduction, and of course needing a membrane to separate water and carbon dioxide and oxygen. This is another need, and then having an electrolyte that is stable, conductive, and has that you can address issues of oxygen solubility and diffusivity. So this remains a problem. And then aqueous lithium air batteries, again, are very attractive, where you can think about going back and forth between lithium metal and lithium hydroxide. But again, you need to have a efficient oxygen evolution reaction catalyst so that you can this has been a problem because most of the oxygen evolution reaction catalysts are again precious metals. Some of the same challenges we talked about when we were talking about hydrogen fuels. Oops. Okay. And then again, you have to optimize the gas diffusion electrode so that you can separate out carbon dioxide, and then need a membrane to block CO2 while allowing oxygen to pass, and then a cheap, efficient catalyst that can mediate essentially this reaction, the oxide to hydroxide formation. This is a big challenge, and so because these challenges remain to be resolved, again, it's a fantastic concept, but the challenge, it hasn't really come to full fruition to the extent that people would like this, that you need for commercial applications, right? And of course, we don't want to have the lithium metal get passivated, so we need a lithium conductive membrane that will protect the lithium and make sure that you don't have lithium hydroxide form on the surface of the anode. Okay, so these lithium sulfur, lithium oxygen are great concepts. Beyond lithium ion concepts, you can still be lithium ion with a lithium metal. That's probably the next big thing coming down the pipeline, and I think there's a lot of excitement about all solid state batteries. But then thinking about this idea of economics, and can you completely go beyond lithium entirely? So fully leave lithium behind. Lithium is here, so obviously you can think about sodium, and there's a lot of work going on here, mostly driven by the idea of economics and having a much cheaper system. And then magnesium, okay, is not just cheaper, but potentially safer if you can more readily solve the dendrite formation problem. It is also has some potential for doubling energy density. So that's a very promising system. And then the fluoride ion. So this is now, so one big concept that a lot of folks are interested in is divalent or really multivalent batteries. So magnesium and calcium or aluminum, divalent and trivalent. And then the other idea is a completely inverted paradigm of an anion battery. So if you can use a +1 ion, could you use a -1, the smallest -1 ion possible, right? So here's an article from Orbach and Yan Yao's group, where they have looked at the potential of different electrodes, lithium, magnesium, calcium, zinc, and as you can see, this is compared it with graphite. So lithium, using lithium metal gives you a little bit more of a potential. Magnesium will give you, and this why magnesium has lower end potential is straight out of your general chemistry electrochemical series, right? Calcium gives you a little bit more. Zinc, of course, gives you a lot less. Lithium metal compared to graphite unlocks, like we talked about, a lot of gravimetric capacity. Magnesium is pretty good, and especially in terms of volumetric capacity, is just absolutely excellent, and so is aluminum, right? And so there's a lot of excitement in using metal anodes beyond lithium, not just lithium metal, but magnesium metal or aluminum metal, and pairing it with the appropriate cathode, right? And a lot of the promise of this derives from the fact that, generally speaking, a lot of these electrodes tend to be a little bit easier to deposit without forming dendrites. And so this is again an article from Yan Yao's group looking at typical morphologies of deposition for different metals, and not as bad as the challenges we have with lithium. So you can consider magnesium typically will be lower voltage for sure as compared to lithium, but again, potentially accessing much higher capacities if we go to magnesium sulfur or even in, paired with different sorts of metal oxide. Most of the magnesium cathode, the one that is perhaps the most well developed, are these extremely good Chevreul phases, and you can get very good stable cycling from these Chevreul phases, MO3S4. The challenge with this is that the voltage is very low, right? Only about 1 volt, but you can get thousands of cycles. There's a lot of interest in coming up with better cathode materials, and that's what I'm going to talk about. From that we've been working in this area that are higher voltage and potentially higher capacity. So the challenge with diffusing magnesium, it's a hotter and more polarizing ion. It's got very different coordination preferences to lithium. So again, a lot of the best work starting from work done by Doran Orbach's group has been in these Chevreul phases. One of the challenges is that the magnesium electrolyte needs to be desolvated at the interface. This is not as much of a challenge for a lithium electrolyte, because if you've got a lithium plus X minus, usually they've been designed to very readily dissociate. But in magnesium electrolytes, and because of the 2+ nature of magnesium, the dissociation oftentimes is into MgCl plus and X minus, and that MgCl bond can be difficult to break, so that desolvation has to happen first before the ion gets sort of into the system, and then it has to migrate to the lattice. These moly sulfide Chevreul phases have been excellent because talk about magnesium being a hard ion based on Pearson's hard and soft acid-base principles. Sulfide being a relatively soft ion is readily distorted as magnesium moves through this lattice. All of the oxide lattices have been less amenable to magnesium diffusion. So there's some work on spinel manganese Mn2O4, sort of MgMn2O4 systems. And again, there's some work going on also with the magnesium sulfide systems. Yesterday, I showed you some of our work on designing cathodes for lithium-ion batteries. We can apply similar ideas to magnesium, but again, keeping in mind that magnesium is a much more polarizing ion, a hard ion, and an ion that can be quite difficult to handle. But again, we've got a lot of diversity in this system because we can access many different polymorphs with different local coordination environments and a range of different structures that we can tune very precisely, and then also a range of different ionicities and covalencies. So what that means is that by tuning the relative ionicity and covalency of the lattice, we can make the oxide ions more more soft or more hard. So this is mostly work done by a very talented recent graduate from the group, Abhishek Parija. And then, of course, vanadium oxides tend to be relatively earth abundant compared to cobalt and some of these materials, right? So again, the alpha V2O5 is the thermodynamically stable phase. We can access this puckered phase through the insertion of lithium and then de-insertion. And this is a gamma prime phase, or we have also double layered these rho phases and delta phases that we can get. And then these two phases are related to each other based on how the layers stack. And through accessing these different phases, we can change the precise pathways that the ions adopt through the lattice. Okay, and so the problem with alpha V2O5, like I talked about yesterday, is that the diffusion path for ions through this lattice is from 8 coordinate to 3 coordinate to 8 coordinate, right? So this is a very large change in coordination environment, and it's essentially impossible for magnesium to go through this. So alpha V2O5, at least at room temperature, is not a very good host for this. Essentially, by looking at some of these other possibilities, you can identify a couple of other options for magnesium and calcium and such. And the change in volume, ideally based on the thermodynamics, should be low, because anytime you have a very large change in volume, you end up essentially having degradation happens very quickly in these systems. So anything in red is really not ideal. Anything that has stayed black on my slide, these numbers are not large. Typically, you want a volume change less than 8%, right? And that's generally true with some exceptions. And sodium ion, because of the large size, is notorious for large volume changes, and this has been a real challenge in trying to incorporate sodium ion batteries. And this is also true for calcium ion. But as you can see, across these structures, magnesium ion can be accommodated with relatively small changes in volume. The second thing to consider from the thermodynamics is the voltage. And the voltage, again, for magnesium is a little bit lower than lithium. But metastable phases, by going to a metastable phase, you can access a slightly higher voltage. And that is because of that is directly a result of the metastability. It's because the metastable alpha MX V2O5 differential with the V2O5 differential, it tends to be higher. So therefore, we can get higher voltage on the other order of about 3 volts. And this is an example of some of these numbers that we get. Just sort of plotted out. And you can see also why people like calcium. It's you can easily access about 3.5 volts here. Okay, so well, metastable phases are all good, but can you actually access these phases? And the answer is yes. You can, if you can be within reasonable range of the convex hull of the most stable constituents, we'll be able to access these phases, and we can actually see that here with a few exceptions. Like I said, magnesium and alpha is very difficult to access, but the rest of these phases tend to be quite reasonably accessible, even though they are metastable. And then moving beyond thermodynamics into kinetics, you can define different pathways. And these are some of the activation energy barriers. As you can see, the activation energy barrier for magnesium is really rather high, but magnesium and zeta and a couple of these structures can be quite low. Okay, and again, using DFT, we can look at these different pathways. Instead of 8 to 3 to 8 in this zeta V2O5 structure, we have a much smaller change in coordination numbers, 5, 3, 4, 3, 5. In this epsilon prime structure, we have 4 to 4 to 4 to 4, right? So we can fundamentally solve the problem of magnesium diffusion by defining the local coordination environments here. And then also based on electronic structure, we can identify hosts that don't have the same problem as alpha V2O5. I'm going to skip through some of these ideas of boulderons that I discussed last time. So we've had the most success with this structure here, zeta V2O5. We take a silver V2O5 and take the silver out by HCl treatment, or we can also start with copper V2O5, and then we can, this is a chemical magnesiation we've done with N-butyl magnesium. We can stabilize this magnesium structure, and then we even have a powder diffraction pattern that is with a Rietveld refinement. And what is exciting about this, we can get about 0.3 magnesium per V2O5, 100 milliamp hour per gram. We can go a little bit higher even at high temperatures, and then we can retain the structure and have an average volt of 1.65 volts, much better than what you saw with the Chevreul phases, and very good reversibility over 100 cycles. Okay, so reasonably good reversibility, and we retain the structure for over 100 cycles. Okay, so this is some probably still one of the best performing high voltage high capacity cathode materials that exist right now. Going back to other magnesium electrolytes, so that's another need is we need electrolytes that will readily desolvate, and so having a weak interaction is especially important. Or also, there's a lot of interest now in designing solid state electrolytes for magnesium diffusion. So a part of this, and I just want to tell you a little story here. I won't take too long because I know we're running a little bit late because of some of our technical difficulties. But part of the case is the story here is the idea that we were very excited that we have a good magnesium cathode, and we wanted to use a magnesium anode, metal anode, because we believe that this is, or there was some claims that this is dendrite free. It's probably true that magnesium is less likely to form dendrites, but let me show you some data that actually shows that magnesium does also form dendrites. So you can see this here very dramatically. Dendrite formation is still proceeding, especially at the edges. And here's an example. This is work by Rachel Davidson. And again, if you looking for, okay. Okay, so yeah, I can play these videos here, and you can see how dendrite formation changes as a function of the current density. Okay, very quick as you increase the current, and the packing of the dendrite also changes, or depending on the concentration of magnesium at low concentrations versus intermediate concentrations. Okay, versus high concentrations. Really spreading out here. So beautiful Christmas trees, but not good news for metal anodes. Okay, so we see different regimes. Again, 2D deposition in certain regimes, this is ideal. Get these large particles in other regimes, and nanowires in some regimes, and then these dendrites in other regimes. And so lots of different factors that control magnesium deposition, voltage, current, concentration, local overpotential, and metal and electrolyte identity. And here's some pretty pictures of the sorts of particles that are deposited. And you can even, in fact, grow large single crystals by this method. These are some examples. The problem that so metal anodes sound like a good idea, especially if you can reduce the propensity for dendrite formation. The challenge, though, is that these metals tend to be much harder than lithium. So one of the strategies we were preventing dendrite formation in lithium is by using a hard separator or a hard SEI, but this becomes even more difficult when you move to something like magnesium, given the large moduli for magnesium. And again, we've done a lot of modeling for this to understand this deposition. How are you going to mitigate dendrite formation? One idea we've gone at is the idea of using these finely nanostructured electrodes, and we can do this using ligand-directed growth of magnesium nanowire arrays. And this, as you can see, this is 500 microns, so very large arrays of nanowires that we can generate here, and across different scales. Or also the other idea is to form hollow magnesium particles and tubes that you can use through galvanic replacement. And so on the magnesium anode side, okay, so anode sizing and structuring is a part of this idea, using shorter diffusion paths, and then that gives you some mechanical stability against cracking. Okay, using two-element alloys is also pretty common, with bismuth, antimony, indium as examples, using micron-sized, in situ formation of nanoparticles of magnesium, and then even liquid to solid transformation. So if you can do this, and if you're using a liquid metal anode, that makes dendrite formation impossible, right? So this is one way to do this. So thinking about batteries beyond lithium, another idea, and I'm just not going to details about this, so we have time for questions, is to completely flip the paradigm and a lot less develop, and come up with fluoride anion batteries that use a negatively charged ion. Okay, so like instead of moving the smallest positive ion, lithium, can you move the smallest negative ion, which is fluoride, through the lattice, right? And there's a lot of work that's been done on conversion chemistry. So, for example, could you take bismuth to bismuth fluoride and magnesium to magnesium fluoride? So you pair a metal fluoride with a metal, so bismuth fluoride to magnesium, and then that goes to bismuth and magnesium fluoride, right? So this chemistry has been explored quite a bit now. It has, again, its challenges. The operating temperature is quite high. These are typically solid-state electrolyte cells. Because these are conversion electrodes, you're converting a metal into a fluoride. There's a very large volume change that reduces cyclability. There's typically multi-step conversions involved, and then the electrodes will often dissolve into the electrolyte, so they're unstable. So again, the challenges with the passivating film. So these are all major problems. Again, the promised gravimetric capacities for these conversion electrodes can be quite high. These are some predictions. Depending on the pair you pick, you can get good conversion. There's relatively little in intercalation chemistry, and this is where we've done some work recently. This is actually published. I haven't updated the citation. This is a compound iron antimonide, where we can, it's got a beautiful tunnel in here, and it's got this lone pair on the antimony, and it's got its iron 2 oxidation state. The iron 2 can be oxidized to iron 3. This is phase pure, and again we can see this by X-ray diffraction. And so the interesting here, and here's the change in the lattice as it expands and contracts. Okay, only slight distortions of the iron and the antimony, so what happens here is again the exact opposite of a battery, right? So of a lithium-ion battery. So lithium ion coming into a cathode will bring about reduction, for instance, of cobalt. Here, the fluoride ion coming into the intercalation host actually brings about an oxidation of iron from 2+ to 3+. Okay, and slight expansion. And so this is work we've done. There's still not very good fluoride ion electrolytes available, but we can do a reaction with xenon difluoride, for instance, and then we can defluoridate as well, and generate do reversible fluoride ion insertion. And what we're really happy about is that we can do this at room temperature, right? So we don't need high temperature. We can do this entirely at room temperature, and you can sort of see this happen. this oxidation reaction happen, and the iron oxide shrinks, the antimony oxide tetrahedron expands. Okay, so I'm going to skip through some of the details here of what exactly happens here. We're writing a paper about this, and it's essentially thinking about how the antimony lone pair helps in this reaction. But you can see here the charge density difference maps, which show that the iron is oxidized, and the antimony actually is not completely an innocent spectator. The lone pair of antimony helps in this in the movement of fluoride ions. So moving towards electrochemical fluoride ion insertion will require coming up with new electrolytes. There's a lot of work in this area, coming up with room temperature fluoride electrolytes, which is going to be critical to do electrochemical fluoridation across these chemistries. And so again, I'm going to leave you with some thoughts here. We've got a whole lot of different applications we need new batteries for. And depending on the application, we're going to have to worry about power, energy, safety, portability, capacity, retention. One, again, emerging technology that I didn't get to talk about very much, but I'm going to show you a brief video, especially for very large area applications, are redox flow batteries. So these are liquid flow batteries that are very good for large areas.
IIT has two tanks. One that is filled with a positive electrolyte.
So this is a great concept of flowing liquids, and you can one of the things you can do with this is you can decouple the power and capacity. This is really great. So in summary, batteries are a major current bottleneck to the renewable energy transition. We need a broad diversity of battery chemistries, not just lithium ion, but also lithium sulfur, lithium oxygen, lithium metal batteries, other metal batteries, even fluoride batteries. And we have to consider about materials criticality and how much do we have each material, what is the earth abundance, what are the criticality supplies. When we need to go beyond hype, I think as we test out these ideas, this is really important. And then interfaces are as important as materials themselves. There's a lot of development that has happened on the solid materials end, but I think a big need is in electrolyte development, which there is a lot of room for organic chemistry and polymer chemistry there. And then these design considerations, again, you can't just think about one material, you have to think about the entire system, and you have to think about the entire system across scales. And we need a diversity of expertise. Okay, so I'm going to leave you with that. No matter what your expertise is, across different forms of chemistry, physics, chemical engineering, material science, electrical engineering, mechanical engineering to tackle these problems. So thank you again, and I'm happy to take any questions you might
have. Thank you, Professor Banerjee, for very interesting talk. And I'm really sorry that due to some shift problem, there is some interruption with the lecture. So I request Dr. Ufana Riaz to please ask the queries of the audience on their behalf.
Hello, Professor Banerjee. So I would like to take up all the questions one by one. The first one is, what are your insights or views on long-term impact on environmental concerns due to improper disposal of lithium-ion batteries as municipal solid waste?
Right. So this is a really good question. I think, the idea of environmental concern starts at the level of mineral extraction. there are a lot of concerns with the extraction of cobalt, for instance, extraction of lithium. What are the environmental consequences of that? And then you saw the complexity of the battery, right? So how many different parts go into it, the packaging. And so extracting elements like lithium and cobalt and other elements from this has and recycling it has not yet become very commercially viable. There's definitely some pilot scale projects going on, and there's a lot of interest in this across the world, in Germany and in the US. There's a lot of folks interested in recycling our batteries, but this the economic viability there hasn't really reached commercial levels. But this is going to have to happen, especially as the number of batteries increase, the size of batteries increases. We have to be able to do some recycling here, and I think this is an open area. Understanding how to extract lithium from e-waste and use it. In this regard, I want one of the big advantages of these redox flow batteries is that they are already recycled and the point is that this is a very simple system as compared to some of the other batteries we're talking about. And there's some exciting work, for instance, out of US Vanadium showing that this is 97% recyclable after 20 years, right? So you can essentially keep reusing, you can recondition the electrolyte and keep reusing it. So I think when we talk about what sort of viable options there are for energy storage in different areas, recyclability is increased. It's going to play an increasing role. And I think this is what makes, for example, redox flow batteries a better option than lithium-ion batteries in these large format applications where otherwise you'll be generating a huge amount of waste.
Okay, so the second question is, what are the basic factors on which we have to work through to optimize the thickness of lithium electrodes, lithium-ion electrode batteries?
Right. So part, I think maybe your question has to do with going from coin cells to pouch cells, and the challenge there is the material balance issues that exist. Oftentimes, in a coin cell, you have a vast excess of lithium and a vast excess of electrolyte, and that's not true as you scale up, and that sets some very practical limits. And this has been especially a challenge for lithium sulfur chemistries. In lithium ion chemistries, I think there is definitely room for improvement there. And as you saw, we are still at only 25% of theoretical capacity. So I think there's room for improvement in the design of their interface and the matching of the electrolyte and the cathode and the anode. And there are some, I think, there are some advances coming. If you saw the quote I had from Dr. Whittingham yesterday, I think even by a factor of 2 in the next 5 or 6 years.
Okay, so the next question is, are there any other characterization techniques other than EIS measurements that can be employed to characterize batteries?
Oh yeah, I mean, absolutely. I think this is a very good point. I focused here on, given the theme of the seminar, on materials chemistry ideas more. There is a lot of measurement science being developed, multimodal measurement in particular, to understand what is going on inside batteries all the way. I think the key idea is to understand, electrochemistry is an incredibly sensitive tool, right? So electrochemistry gives you signals that are pretty exquisitely detailed in terms of, the events happening, at the level of a few electrons, right? But the challenge is to understand what those signals mean in terms of structure, right? And materials, like what exactly is happening to the material when you see a certain electrochemical signal. So this is why I think there's a need for operando electrochemical characterization that is coupled to materials characterization. And there's some beautiful work on, for instance, operando electron microscopy, operando X-ray spectroscopy, neutron diffraction, MRI methods that are basically helping us understand what exactly do these EIS signatures, these electrochemical signatures, actually mean, right? You know, the thing with EIS, the data is very rich. The data is very, detailed, but understanding the data can be quite difficult because you are essentially doing circuit modeling and your circuit may or may not be, correct. And so having structural tools coupled with electrochemical tools is, I think, going to be critically important. The other advantage is the idea of using machine learning and learning from lots of data to basically start getting a better intuition for what the electrochemical methods are showing us in terms of actual structural changes.
Okay, so the next question is, upon mitigating the dendrites growth by electroplating with soft substrate, how will the mechanism work?
Right. So the idea is that you have these trains that develop because you've got an SEI and you've got a volume expansion of the SEI, right? And then you have a volume expansion of, so you've got a sort of a mismatch and stress generation at the interface of the lithium metal and the SEI. And one concept is, could you use a soft substrate where the strain from the lithium volume change will be accommodated by the substrate rather than by the SEI, right? So you're going to have less crack formation at that interface, and so you'll have a more robust and mechanically resilient SEI because you dissipate some of the stresses into the substrate. So that's the idea of using a softer substrate.
Why fluorination by metal catalysis is rare in limited substrates?
Yeah, so the metal conversion electrodes, right? So the biggest, if I understand what you're asking, yeah, so metal fluoride chemistry depends on the primary impediments are what are you going to use as the electrolyte and what are the kinetics of that reaction, right? It's a conversion reaction, right? And it typically requires an overpotential, and there's a hysteresis between charge and discharge. So these are all issues. People have identified reasonably good couples that some of them even work at room temperature, but again, these kinetic issues are still a problem for conversion chemistry.
The next one is, should we select porous electrode materials over solid ones? As far as porous materials are considered, which among COF and MOF is better electrode material?
Well, I mean, the porous electrode, this really depends on if you're trying to get high volumetric capacities and such. Well, you'd like to have reasonably dense electrodes, right? But our current electrode architectures are quite porous, right? And that's essentially to alleviate some of these mechanical stress issues that we're talking about. Otherwise, you would have much more cracking. You also want to have some good electrolyte contact. That is also a major issue. But ultimately, I think we'd want to move towards electrode structures that are as dense as possible. Again, in the case of lithium air, lithium sulfur batteries, it's porous again so that you could have good electrolyte contact and relatively small diffusion path lengths. So the idea of COF and MOF, it just really depends on what sort of diffusion pathways are available in a specific structure and what sort of electrolyte permeability there is if you want to use it as an electrode, what sort of gravimetric capacity you get. COFs typically being entirely organic, right? It can give you some, are extremely lightweight so that you can get very high gravimetric capacities, but the volumetric capacities tend to be a lot lower, right? Because they usually, the electrons stored per unit volume tend to be lower, right? So there's, I think, pros and cons to each of these. The cyclability can be a challenge in organic systems, how long they survive and how resilient they are to cycling. But again, all of these are challenges that, these are also relatively new materials and people just need to work more on overcoming these challenges.
The next question deals with the characterization. How do battery characterization in terms of EIS and stability tests help us to design new materials?
Right. So, I mean, I think the EIS, especially as, there's a lot of interest in understanding. So on the one hand, you've got fundamentals of battery chemistry. Okay, we can write reactions that happen at the cathode. We can write reactions that happen at the anode. And that's, not so difficult to do, right? But like I was talking about 2 days ago, if you go in the lab and you run a reaction and you get a reaction yield of 90%, right? That's really great. You'd feel like you're a pretty good chemist. But if you have a reaction rate of 90%, right, and in an electrointercalation reaction, over 2 cycles, you're down to 81% capacity. Over 3 cycles, you're down to 72% capacity, right? So essentially, you very soon have a battery that doesn't work, right? So what are the degradation mechanisms, right? This is really, really important, right? And the degradation mechanisms that happen could be parasitic reactions. They could be chemomechanical in origin, right? The coupling of chemistry and mechanics. They could have to do with, either the cathode or the anode. So when you have a whole cell impedance signal, trying to understand what exactly is going on that is causing these changes can be quite difficult. So impedance is, I think, part of the story, but it's really important to interrogate, structurally what is going on at the cathode and the anode and at the interfaces. We talked about the SEI. Still lots of open questions about the structure of the SEI, how to control the structure. It's pretty clear now that there is something similar to SEI at the cathode. The CEI is what people call it, and that's also important. So understanding that is going to be critical to understanding things like irreversible capacity fade. What are the fundamental things that affect rate performance in these systems?
What are the characteristics in the EIS measurements that we should look for to have a better electrode material?
Well, again, like I said, I would say EIS is not the be all and end all. You have to look at structural characterization, EIS and just cycling discharge data can give you a lot of information at different rates, but it's not everything.
I guess these were the questions that we had today. So thank you, Professor Banerjee, for the extensive research that you have presented on lithium ions and its perspectives in designing electrodes and the future prospects. We've covered the commercial viability aspects thoroughly, which were very well explained, and the presentation has been very descriptive in terms of the graphics and the data that you have shared, and even the videos that you have shown. I guess a huge effort has been put in designing such a wonderful presentation, which was intense yet very interesting. Thank you for keeping our spirits very high, and we are looking forward to your future lectures. Thank you, Professor Banerjee, for spending a wonderful time with us, for sharing a wonderful information and interesting and very useful for our postgraduate, undergraduate, and even our research scholars who are attending the lecture very attentively. Thank you so much for being with us.
Thank you, Dr. Riaz, and I look forward to tomorrow's set of lectures. Thank you.